So now here I want to do another example of a quadratic equation. So what I do is I take A1, A2, A3 as three independent uniform 0, 1 random variables. And then I want to consider the quadratic equation A1x squared plus A2x plus A3. Okay. Now here I ask a question, when are the roots real? Right. So notice one thing is important, notice the coefficients are random, right? Let me make it bigger. So coefficients are random. So it's natural to ask, when are the roots real, right? So maybe the correct question perhaps is to ask, I'll move this across, I'll move that here. So I have to remove this. Maybe the correct question to ask is the following: what is the probability the roots are real, right? What is the probability that the roots are real? And the probability comes in because the coefficients are random. Okay. Now we know from your 12th class that the roots are real when A1 squared, A2 squared minus 4A1, A3 is non-negative. Right? Right. So that's the same as the 12th class formula that B squared minus 4AC is non-negative for this quadratic equation. Right. Now, now all I do is I have to find the probability that this event happens, that is A1 squared minus A2 squared minus 4A1 A3 is non-negative. So when does this happen? When now we know that all the AIs are between 0 and 1 because the uniform 0, 1, that's what we chose it as. Very nice. Now this equation 1 will hold if you just observe a little bit. See, this guy has to be less than a quarter because otherwise it will force A2 to be bigger than 1. So I have this condition, and the other condition is I need this condition to hold, that is 2 root A1 A3 is between A2 is between this and 1. Only when both these conditions hold will 1 hold. That's the first reduction you have to think about. Okay. Then you split up into two cases, this part. One case is when A1 is between 0 and a quarter. In this case what happens, A1 A3 will be less than a quarter no matter what A3 is, because A1 is less than a quarter, because A3 can be at most 1 and non-negative, so this is always satisfied for any A3. Similarly, if A1 is bigger than a quarter, then you have to worry a little bit. A1 A3, this will be A1 A3, I should put A1 here, this A1 A3 here is less than a quarter only when A3 is between 0 and 1 over 4A1. That was not satisfied. So now you have classified all the cases of when how 1 will occur. So you start from here, then you split this up in two cases, and each case you split up separately for A3. Right? So now the next step is to find the probability of that event. For that you need a joint density of A1, A2, A3. Now we know the marginal density of AIs are uniform 0, 1. So it's 1 when x is between 0 and 1 and 0 otherwise. And the joint density is simply a product of the marginals, because if you have random variables independent, then the product of the marginal densities is the joint density, right? So that's an equivalent condition of independence. So use that fact to get this formula for this thing. Now you go to this event. You're interested in probability the roots are real. That's the same as the probability that the random variables satisfy this condition. Now this we have already done in two cases, right? One is when A1 between 0 and a quarter, then A3 can be anything, and A2 has to be between 2 square root A1, A3 and 1. Similarly, when A1 is between a quarter and a 1, we know that A3 has to be between 0 and 1 quarter 1 over A1, 1/4 of A1, and A2 has to be between this number and this number. Now you have an OR here. So, and we also note that if this line happens, then this line cannot happen, and vice versa. If this line happens, this line cannot happen. So they are both mutually exclusive events. So the probability is the sum of the two probabilities. Let me write this down just to sort of reiterate it. So they are mutually exclusive events. once you have this, you have these two probabilities. Now this implies that all you have to do is find the probability of this region happening and this region happening. Now we know again by standard facts that, so this, let me write this down in orange. We know the fact that probability that A1, A2, A3 is in a set C is just given by the triple integral over C of dA1, dA2, dA3. And maybe I'll just write this a little bit bigger, so it's sort of move across, and then so this means here, and then I'll just move this across here. I'll have a F of A1, A2, A3. Right? The joint density of this guy. That's what it's going to be, right? So let me just mark this in pink. Sorry about that. Let me just mark this in orange. Yeah, that's what it will be. So maybe I call this as F sub A1, A2, A3 as well, the joint density of this one. So maybe I'll erase this and just think of this as, this is just the joint density. Joint density. And we know that's just uniform, so it's going to be 1 when all the AIs are between 0 and 1 and 0 otherwise. So already my set is designed so that everybody satisfies that condition, so there's no problem here. So I come here and I plug in those numbers. So A is A1 between 0 and a quarter. If I look at this calculation right here, and a quarter, and A2 between 0 and 1, and then A2 is between these guys. So I have this guy. And then second case, I do the same thing again. I have 1 quarter, I have 0 and 1 quarter A1, and then I have this other person right here. So once I have these three things, I just do the calculus after that. So the first case, what I do, in the first case, I have a, so I should make it a little bit more precise here. I have a, yeah. So the first step is quite easy because all I have to do is integrate out 1 over for A2. That's quite easy because A2 just 1 means it's a constant function. So just put the limits in. So I get 1 minus 2 root A3 here. And here I get 1 minus 2 A3 again. Same thing. There's no problem. These two integrals are the same. Right? Second step is when things start. I have an integration over A3. So which are colored in orange. A3 goes from 0 to a quarter A1 in the second integral and 0 and 1 in the first integral. Right? The simple calculus exercise, you can just do this. If you keep A1, 2 and 1 constant, then just an integral of a square root, and that will give you 1 minus 4 by 3 a root A1, the first guy. The second one is a little bit more complicated because the limits of integration are 0 to 1 over 4 A1, so you get something like a little bit more complicated than this. dA1. And you can finish the integral to get this following answer. So this is the chance that the roots are real if you have A1, A2, A3 being uniform 0.